Yes, it's Uncle Chegs, and in today's video we'll be looking at the enzymes required practical for the GCSE science specification. I'll be dividing this video into these sections, yeah? Number 1, what is a protein? Number 2, what is an enzyme? Number 3, what affects enzyme activity? Number 4, the required practical, and then finally number 5, possible questions that you may get. As always, check out the timestamps below to skip to exactly what you want to hear, and also download the worksheet for this lesson and the answers to last week's lesson as well. Alright, let's do this thing. You have 3 major macronutrients. Macro comes from the Greek word for large. We need these 3 macronutrients in large quantities. The first one is fats. These are used for energy and insulation. The second is carbohydrates, which are also used for energy. The 2 carbohydrates that we are concerned with today are starch and glucose. And finally, we have proteins. These are used for growth and repair. Looking closely at a certain type of protein, we see that it is folding into a specific shape. If you remember anything from my video on specialized cells, you remember that structure equals function. This also applies to proteins, and it's their shape and interactions that give them their function. Now let's look even closer at this protein. We see that it's made up of bare amino acids linked together. This here is a typical structure for an amino acid, and the geek gang out there, you've probably clocked where the name comes from. Over here you have an amino group, and over here you have an acid group, amino acid. Now these amino acids link up by losing an OH from the acid group and a H from the amino group of the other side. And this forms a peptide bond and a water molecule as well. Notice that we still have an amino group on one side and an acid group on the other side, so even more can link up. You have roughly around 20 naturally occurring amino acids. Each has its own specific R group, and it's this R group that gives amino acids their special features. I'll break these into 4 main groups. Number 1, non-polar, which means there's no charge whatsoever anywhere. Number 2, polar, which means there's a slight charge on it somewhere. Number 3, positively charged, which means there's a permanent positive charge on it somewhere. And finally, number 4, negatively charged, which means there's a permanent negative charge on it somewhere. So linking these in a random order, they will naturally fold, just like magnets attracting and repelling each other. The different R groups attract and repel, creating a 3D structure that gives proteins their function. Remember these bonds and attractions for later because they'll come important later, okay? Now, one of the most important classes of proteins in your body are enzymes. They speed up chemical reactions without being used up. This is important for metabolism. If you have no enzyme, so if I took all the enzymes out of your body, your chemical reactions will take too long and you'll die. The model for enzyme activity that you need to know is called the lock and key model. This is when the enzyme and substrate fit together like a lock and key. The substrate is essentially your reactants, but the technical name is substrate, so use that, yeah? When they join up together, they form an enzyme substrate complex. And due to the forces of attraction on the enzyme and substrate, the substrate changes either by splitting apart or joining up to make a bigger molecule. Notice that it's the substrate that's changing, yeah? Your enzyme hasn't changed and is ready to bind another substrate. You have thousands of chemical reactions going on at the same time in your cells. You need a specific enzyme for each of your reactions. The enzymes differ in the shape of this location called the active site. This is the name that you mention for the unique shape where the substrate binds. Now let's look at a couple of these enzymes that you need to be aware of and also where to find them in your body. Starting in your mouth, mixed in with your saliva, we have an enzyme called amylase. The shape of this enzyme allows it to break down starch into simple sugars. However, you also have amylase in your small intestine. So to distinguish between the two, we call the one in your mouth salivary amylase, okay? When you move down to your stomach, we have a protease. Geek gang may already know what this breaks down. It must break down proteins. Remember that proteins are made from amino acids. Well, protease break down our proteins into amino acids again. And now we move down to your small intestine. Here we have amylase, as I mentioned before, but you also have a protease in here as well. And finally, you have a lipase. Lipase acts on lipids. Notice a trend in how we name our enzyme. They all end in A's. Lipids are fats if they're solid at room temperature, and oils if they're liquid at room temperature. Lipase breaks them down into a molecule of glycerol and 3 molecules of fatty acids. Now here's some summary notes of all of that information, yeah? Pause the video, make sure you understand all of that before we move on. Now we've seen what enzymes do under normal conditions. There are 2 main things that can affect how well your enzymes work. This is called the enzyme activity. It's plotted on a graph that looks like this. Enzyme activity goes on your y-axis. The factor that's affecting your enzyme goes on the x-axis. You would normally see one of these 2 shapes. The peak of the hill is your optimum condition. These 2 conditions are pH and temperature. Let's tackle temperature first, since that's the easiest to pattern. At low temperatures, the particles aren't moving as fast because they have a low kinetic or movement energy. This means that they are less likely to collide with the substrate, meaning there's a lower rate of reaction. When we increase the temperature, the particles are moving around faster, meaning that they are more likely to collide with the substrate and allowing a chemical reaction to happen. Then we get to the peak of our graph. This is where your enzyme works the best, our optimum temperature. Optimum, like Optimus Prime, just means the best. And then we get a decline over here. This is when we start to break the bonds in our enzyme, which changes the shape of our active site, so the substrate can no longer fit in. We have denatured our enzyme. Literally, we've taken away its nature. And the nature of an enzyme is to speed up the chemical reaction. Something similar happens with pH. pH is a measure of the concentration of hydrogen ions and hydroxide ions that you have in your solution. If you remember, some of our amino acids are polar, or they have a permanent charge on them. These charges can be changed by changing the pH, so you've denatured your enzyme since the substrate can no longer fit properly into your active site since the forces of attraction have changed. Here are some summary notes of all of that, and then we're going to move on. For your required practical, you are likely going to investigate the effect of pH on the rate of reaction of amylase enzyme. Jaden,
Huh?
remind us what our variables are.
That D my thing, innit?
Yeah?
Dependent measured y-axis.
Cool. So what are we measuring in this experiment?
The amylase, innit?
Yeah, but what about the amylase? Look at the statement again.
The rate of reaction.
Very good. We're measuring the rate of reaction of the amylase enzyme. So finish us off. What are we changing?
pH.
Perfect. Tatiana,
Yes, uncle?
what should be our control variable based on what we are measuring and changing?
Well, we're measuring the rate of reaction and changing the pH. You said that pH and temperature affects the enzyme, so we have to keep the temperature the same to make it a fair test.
Fantastic answer. If you remember from earlier, amylase turns starch into simple sugars. To monitor the change from starch to simple sugars, we need to use iodine. This is what a drop of iodine looks like by itself. This is what it looks like when we mix it with sugar. And this is what it looks like when we mix it with starch. As you can see, iodine goes purple-black with starch. And since amylase is meant to break down starch into iodine, if our solution goes purple-black, this could mean that our enzyme is denatured, or simply we haven't left our enzyme in the solution long enough for it to start acting. The dependent variable here is the rate of reaction, how long it takes the starch to break down into simple sugars, which we will be observing by checking how long it takes the purple-black color not to be present anymore. These are the steps. Number 1, you add a drop of iodine into each depression in your spotting tile. Number 2, you add your different pH solutions into separate test tubes. In this example, I'm using pH 5, 6, 7, and 8. Have one of your amylase and have one for your starch solution as well. Number 3, place your test tubes into a water bath at 35 degrees Celsius. Number 4, you add 2 centimeters cubed of your first pH solution into another test tube. Number 5, you add 2 centimeters cubed of your amylase into the same test tube. Number 6, you use another syringe to add 2 centimeters cubed of your starch solution to the same test tube. As soon as you do that, number 7, you start your stopwatch and leave the time running. Mix your test tube using a glass rod, that's number 8. Number 9, after around 10 seconds, you add your drop of your mixture into the first depression in your spotting towel. Number 10, you rinse your rod and you keep repeating these steps until the iodine stays orange. This means that the starch has been broken down. There's no more starch in the solution. Repeat these steps with your other pHs and then you record your results in a table like this one. In the worksheet for this week, I have 2 questions based on data from a similar experiment. The first one has a results table and asks you to work out the mean. For this, remember not to include any anomalies in your calculations, okay? The second one has a graph and asks you to describe the graph and then explain the trend after pH 7. Humans need to start being more independent. So that's all the clue I'm going to give you. Have a go at this and check your answers in the next week's video, okay? So yeah, that's all I've got time for. Like if you like, subscribe if this is something necessary in your life, and yeah, in a bit.